Hello, this is a review of Chapter 2. So we're going to work through some of the problems that will demonstrate most of our main concepts from this section. Let's go ahead and get started. All right. First of all, we want to find the intercepts, vertex, and axis of symmetry for this quadratic function. F of x equals x squared minus 4x plus 3. To start with, let's remember, if we can put this function into standard form, it would look like f of x equals a times x minus h squared plus k. And if we can get it into this form, then the vertex would be hk. All right, so this one doesn't look too bad to change forms. Let's go ahead and for this function f of x, I will put some parentheses around the x squared minus 4x. So we have f of x equals x squared minus 4x. And I'm going to leave a little extra space in here. And then we have plus 3 after the right parenthesis. Okay, so what I want to know is what number can I add here to complete the square? Because I'm going for x minus h squared here. And to complete the square, if I have x squared minus 4x, what I'm thinking of is writing x squared minus 4x as x minus 2 times x minus 2. So that my middle term would be minus 4x. That means my final term here would be negative 2 times negative 2, which would give us plus 4. So the number that I want to put after the minus 4x is plus 4. I can't just go adding numbers to a function, though. That would change the function itself. So if I add 4 here, I want to subtract 4 to the right of the 3. So I'm keeping the balance of my function. And so now once we've got our function ready to complete the square, we'll go ahead and work on completing the square. We can write x squared minus 4x plus 4 as x minus 2 squared. And then I have minus 1. Okay, so our function is in the format that we were looking for. A here would be 1, h would be 2, and k would be negative 1. So our vertex, which is hk, is going to be 2, negative 1. All right, so we found the first thing that was asked for. Well, actually, I guess the second thing that was asked for. The third thing that is asked for here is the axis of symmetry. That's really easy to get once we have the vertex. For the axis of symmetry, all we do is look at that x coordinate of the vertex, and the axis of symmetry is a line. It's going to be the line x equals 2. We'll put this on a graph in just a minute, so this will make more sense. And then the other thing we're asked to find here is the intercepts. For the intercepts, we have x-intercepts and we have y-intercepts. Let's start with the x-intercepts. And to find the x-intercepts, we set y equal to 0 in our original function here. So we're going to have 0 equals x squared minus 4x plus 3. I can factor the right-hand side of the equation here into x minus 3 times x minus 1. And we set each factor equal to 0, giving us x-intercepts at x equals 3 and at x equals 1. We like to write intercepts as ordered pairs, though. So we would write these x-intercepts as the ordered pairs 3, 0 and 1, 0. Okay, so we have the x-intercepts. We still need the y-intercept. To find the y-intercept, we set x equal to 0. And that means we're going to end up with y equals 0 squared minus 4 times 0 plus 3. Or y equals 3. Again, as an ordered pair, this would be the point on our graph 0, 3. So we have found everything that was asked for here. We'll move on to our next slide, where we're actually going to use this information that we've found to graph the function. Starting with, well, actually, I like to start with the vertex. The vertex is 2, negative 1. So let's put that point on our graph. the axis of symmetry is x equals 2, which is just the vertical line that goes through the vertex. So let me put this on here. Okay, so this is the line x equals 2. Usually we use a dashed line here because it isn't really part of the graph, but it's an important aspect about the graph. And then we'll throw the intercepts on here, 1, 0, 0, 3, and 3, 0. Oh, wait. Oh, okay, what did I do? So 1, 0 is right here. 0, 3 is right here. 3, 0 is right here. So I'm not sure quite what I was doing there, but anyway, this works. So we have these 4 points. What I kind of like about that axis of symmetry is that tells me that if I have a point on one side of the axis of symmetry, there's going to be an identical or a matching point that's the same distance away from that axis of symmetry on the other side. So that means I can add this point 4, 3, and that 0.43 is going to make my graph look a little better, I think. So let's go ahead and connect these dots in a nice smooth curve. Whoa, okay, I missed going through the right point there. It's kind of hard getting good graphs with my apparatus here. Okay, so let's again aim for a nice smooth curve that hits all the points that we need it to. Okay, well that looks a little bit wavy there, but let's see, maybe I can clean it up just a little. Oh, that looks better. Okay, so here is kind of like a parabola. It looks as smooth as I can get it right now, and this is a graph of the function f of x equals x squared minus 2x minus 3. Okay, let's move on to number 2 here, where we want to identify the vertex, and then we're going to determine if that vertex yields an absolute minimum or an absolute maximum. For this function, we have f of x equals negative 2x squared plus 4x minus 5. We could put this function into standard form, but I wanted to show you another method of finding the vertex. If we have our formula, or our function in the form f of x equals ax squared plus bx plus c, then we can find the vertex using the x-coordinate of negative b over 2a, finding what that is, and then plugging our x-coordinate into the function to determine what the y-coordinate would be, which we can refer to as f of negative b over 2a for the moment. Okay, so we can find the vertex this way if we just leave our function in the general form. And it looks like in this problem, it might be a little bit easier to do. We need to figure out what a is. Here a is negative 2, b is 4, and c, which we don't really need at the moment to find the vertex, c is negative 5, right? Okay, so let's go ahead and find negative b over 2a, and that would be equal to negative 4 over 2 times negative 2, or that gives us 1. So the vertex is, the first coordinate of the vertex is 1. We need to figure out what the second coordinate is by taking that x value of 1 and plugging it into our function f of x right here. So we're going to basically be finding f of 1, which would be negative 2 times 1 squared plus 4 times 1 minus 5. We get negative 2 plus 4 minus 5, so that would be 2 minus 5, negative 3, if I did that correctly here. And so our vertex is going to occur at the point 1, negative 3. Okay, so we have the vertex. We want to know if this vertex yields an absolute minimum or absolute maximum, and this is where a being equal to negative 2 gives us some information. So if a is negative 2, if a is negative, that tells me that my parabola is going to open downwards and that the vertex is going to be here at the top. And so I would say that my vertex would yield, in this case, an absolute maximum here. So we can say the vertex yields an absolute maximum, the highest point on our graph. Okay, and let's move on. Sam plans to build a rectangular pasture with 400 linear feet of fencing material. If the pasture is adjacent to a stream so that no fencing is required on that side, what are the dimensions of the pasture that will maximize the area? So let's start with a sketch. And we'll use like blue for the stream water. And we'll make our fence. I don't really have any brown, so what color should we make the fence? I don't know what this first color is. It kind of looks black. Let's see. Yeah, it is black. That works. Whoa, this isn't looking good though. Even though my stream looks a little bit wavy there, in math we try to have everything at right angles, and so I'm going to pretend like we come out the same distance down here, and we have a nice rectangular area here. Okay, where we're saying that, we'll say that this width here is x, this width is the same width x, and then we have a length y, if we think of it that way. Okay, so doing good so far. We have our picture drawn. And the next thing I want to look for is an objective function. Well, what is my objective? My objective is to maximize the area. So my objective function is going to be a equals something. And let's say a equals, well, any rectangle we should be able to find the area from by taking the length times the width. So here we can just say our objective function is area equals x times y. And then another function that I like to find, or another equation that I like to find, I should say, is the equation that constrains how big I can make that fenced-in area, because we only have 400 linear feet of fencing here. We want to use all that to make our area as big as possible, but that 400 linear feet of fencing is going to have to cover this first length x plus this length y plus this length x. All in all, we could say that 2x plus y is going to equal 400. Okay, so we have our objective function and our constraint. I'm going to go ahead and jump to solving this problem. The first thing I'll do is solve my constraint for y. So y equals negative 2x plus 400. And then for my area function, which I'm trying to maximize, I'm going to replace the y with what y is representing here. So I'll replace my y in my area function with negative 2x plus 400. The primary reason for doing that is that I can get my area function totally in terms of x. And then I'm going to have a equals negative 2x squared plus 400x. Now we can see that we have a quadratic function. And for a quadratic function, we can find, in this case, if I graph this function, it would be opening down because I have a negative coefficient on the x squared term. If my function is opening down, that means the maximum area is going to occur at the vertex. So our goal here is to find the vertex. If you remember a minute ago, we found the vertex of a function by taking negative b over 2a for the first coordinate of the vertex. For this function, and I have a big A and a little a here, my little a is going to be the negative 2. My little b is going to be the 400. So to find negative b over 2 times little a, I'm going to take negative 400 over 2 times negative 2, and so that would give me 400 divided by 4, or 100. So my vertex occurs at the point where x is 400. Oh, I'm sorry. I mean where x is. So my vertex occurs at the point where x is 100. Okay, let's change that. So we have 100 something or other. So So we don't know quite yet what the area is at that point. But you know what? We're not even asked to find the area. We're asked to find the dimensions of the pasture, which is even a little bit easier because I can easily come back to where I solved for y here. And when x is equal to 100, which is going to be when our area is maximized, y would be equal to -2 times 100 plus 400. That gives us a y value of 200. So my dimensions that will maximize the area are 100 feet for the width by 200 feet for the length. So this y would be 200, x would be 100. Altogether, that adds up to 100 plus 200 plus 100 gives us the 400 feet. So this is the answer to the problem. If I wanted to go ahead and find the area, it wouldn't be too hard. I could find it in two different ways. I could plug this 100 back into my original area function right here. Or I could just, probably even easier, I could find the area by taking 100 by 200. So what would we get there? We'd get 2,000,000, 20,000 square feet. Okay, I think that's right. All right, so this would actually be the maximum area. Okay, so let's move on and let's look at our next problem here before there's not too much more we can do with this one, I guess. So our next problem is, this is an equation that's quadratic in form. We're asked to solve x minus 2 square root of x minus 3 equals 0. Okay, you should have done some of this probably in Math 1010 if you took Math 1010. But if not, let's look at what we're trying to do here. We usually try to do a u substitution for these equations that are quadratic in form. In this case, if I let u equal the square root of x, what do I get if I take u squared? So u squared would be the square root of x squared, and so in this case it would just be x. Okay, so I can replace my equation of x's with turning the x's into u's by replacing x with u squared. That means I have u squared minus 2 times u, which is square root of x, minus 3 equals 0. One advantage to doing this u substitution is that it makes factoring a little bit easier. And so now I can factor my equation into u minus 3 times u plus 1 equals 0. Going back to plugging in these x's, which is what we're really trying to find, I would have, well, I'll go ahead and solve for u, and then I'll replace the u's with square root of x. If I solve for u, I'd set u minus 3 equal to 0 to get u equals 3. I'd set u plus 1 equal to 0 to get u equals -1. Either one of these u values will give me a solution to the equation here. And then I go back and replace u with square root of x. If square root of x equals 3, then I can basically square both sides to give me x equals 9. Okay, so if square root of x equals 3, I can square both sides to give me x equals 9, and that makes sense. If I take the square root of 9, I get 3. Okay, so I have a solution of x equals 9. What about if square root of x equals -1? Well, as long as we're talking about real numbers here, there's no real number that I can take the square root of and get -1. The square root of a positive number is all that we can take right now, and the square root of a positive number is going to be defined to be the positive square root. So square root of x equals -1, we don't get a solution from that. Okay, and you might work some more of these problems. I think probably in your homework you have a few of these that you can practice with. Moving on then, we want to find real zeros and multiplicities and graph this polynomial, which is f of x equals 2 times x minus 1 times x plus 3 squared times x minus 4 squared. So it's fairly easy to find these zeros. To find the zeros, we would look at what values for x would make our factors equal to 0. So there's no value for x that's going to make 2 equal to 0, right? To make x minus 1 equal to 0, I could let x be equal to 1. For x plus 3, I could let x be equal to negative 3. For x minus 4, I would let x be equal to 4, and these would be my zeros. Okay, what we're wanting to also look for is the multiplicities of these zeros. And for the multiplicity of x equals 1, since x equals 1 comes from the factor x minus 1, and this factor is raised to the first power, my multiplicity is 1. X equals negative 3 comes from the factor x plus 3, which is raised to the second power. So the multiplicity is 2 here. X equals 4 comes from the factor x minus 4, which is raised to the second power, giving us a multiplicity of 2 there as well. So we have the real zeros, we have their multiplicities, we want to graph the polynomial. There's one more thing I need to know. I either need the end behavior of this polynomial or I need to grab a y-intercept. And in this case, it looks like a y-intercept would work. So let's go ahead and find the y-intercept here. The only time a y-intercept doesn't work is when our y-intercept is at the origin, which it's not going to be here. So we can find a y-intercept. To find the y-intercept, we just set x equal to 0. So we have y equals 2 times 0 minus 1 times 0 plus 3 squared times 0 minus 4 squared. We get y equals 2 times negative 1 times 3 squared is 9 times negative 4 squared is 16. And that gives us y equals negative 288, I believe. So we have a y-intercept at the point 0, negative 288. Okay, let's go ahead and see if we can graph this polynomial then. All right. So let's start with our 0 at x equals 1. Okay, I'll put that little dot on the graph. Having a multiplicity of 1, 1 is an odd number, which tells me my graph is going to cross at the point x equals 1. Looking on down, a multiplicity of 2, 2 is even. And so my graph will simply touch and bounce at both x equals negative 3 and x equals 4. Okay, so we'll keep that in mind as we start graphing. We have another 0 at x equals negative 3, and a third 0 at x equals 4. Okay, our y-intercept, which as you notice, I didn't put tick marks on the y-axis because this is like way down here somewhere at negative 288. Okay, we have it pretty much set up. So the reason I want that y-intercept on there is that my graph is going to have to come down below the x-axis between x equals negative 3 and x equals 1. I think I'll start by trying to, I'll go through this y-intercept and then I'll come up and I'll cross at x equals 1. If we go to the right to x equals 4, we're going to simply touch the graph and bounce at that point. So to the right, our graph will go like so. Now that we don't know that there's a minimum at y equals negative 288, we just know it's a point on our graph, and so my guess is it probably is not a minimum value. So we probably, we might come down and then we're going to come up and we're going to bounce off the x-axis at the point x equals negative 3. It looks like I didn't hit that real well there, but this is what our graph would look something like this. What we're interested in is am I hitting my intercepts correctly? And is my graph above the x-axis when it should be above the x-axis? And is it below the x-axis when it should be below the x-axis? So if you've got that, and if you have a nice smooth curve, you can probably get it smoother than mine, then you're good. So that's what we're looking for with these problems. If I see something that looks too far off of this, I'm probably going to guess you had some electronic help with that. So just do your best with these, exactly like I solved this one. All right, so let's go on to another problem. In number 6, we have a polynomial, and we're told that the polynomial has a 0 of 4. We're asked to use this 0 to find the other real zeros and to factor the polynomial. So this is kind of a nice trick we can use here. If we know that we have a 0 of 4, we can actually divide this polynomial g of x by x minus 4. Remember, if x equals 4 is a 0, then x minus 4 is a factor of the polynomial. To divide by x minus 4, I'm going to use synthetic division. I'll put 4 in my little box here. To the right of my 4, I want to write the coefficients of g, which are 3, -7, -22, and 8. Okay, so I'll put those numbers here. And then I'll put a little space, draw a horizontal line, bring down the 3. 4 times 3 is 12. -7 plus 12 is 5. 4 times 5 is 20. -22 plus 20 is -2. 4 times -2 is -8. 8 plus -8 is 0, which is what we want here. We've just now not only found that x equals 4 is a 0, or verified that, we've also factored polynomial g of x into x minus 4 times 3 times, I dropped the degree 1 to give me 3 times x squared plus 5x minus 2. And now hopefully we can factor that quadratic so I don't have to mess around with the synthetic division anymore. And it looks like it would factor into 3x something times x something. We're wanting a 5 in the middle, so I'm thinking probably a 2 goes here and a 1 goes here, and that 5 is positive. So you may have to just mess around a little bit, but once you have it, what you think are factors, let's double check. So we'll FOIL together 3x minus 1 times x plus 2. I get 3x squared plus 6x minus 1x gives me the plus 5x in the middle. And then -1 times 2 gives us this -2. So g of x is factored. This is one thing we were asked to do, to factor the polynomial. So I'm going to call this part of my answer. And then to find the other real zeros, I would probably go ahead and list all of the zeros. The zeros are x equals 4, the first one we found. From the factor of 3x minus 1, if I set this factor equal to 0, I find a second 0 of x equals 1/3. And then from the factor x plus 2, setting that factor equal to 0, I get a third 0 of x equals -2. Okay, so my zeros are -2, 1/3, and 4. And we've got this one. All right, let's move on to number 7 here, where we're asked to use the rational zeros theorem to find the potential rational zeros of the polynomial f of x equals 3x cubed plus 17x squared minus 12x minus 15. And note here that you're not asked to do any solving for zeros or any factoring or anything. In fact, I just made this one up, so my guess is it's unlikely that any of these rational zeros would work, but who knows? Okay, so how do we find the rational zeros? Well, we're going to look for some numbers. This number, this constant number on the end here, -15, is where I'm going to grab my values for p from, which we'll talk some more about in a minute. The coefficient on the highest power term, 3x cubed, which is 3, this is where my values for q are going to come from. So if we have rational zeros, the rational zeros are going to be of the form p over q, where the p's are factors of -15. For example, if we take -1 times +15, we get -15. If I take +1 times -15, I get 15. If I take 3 times negative 5, I get 15, or negative 3 times positive 5, I get 15. Okay, so any of those numbers that we're multiplying together there would work as numbers that we need to include for possible rational zeros here. Okay, so my p's are going to be, and to be kind of lazy, I'm just going to put plus or minus out here in front. Plus or minus 1, 3, 5, 15. Okay, so we've taken care of all the integer factors of negative 15. Let's look at q. So what numbers could I multiply together to get 3 here? So 1 times 3 would work. Negative 1 times negative 3 would work. So for q's, I'm going to have plus or minus 1, plus or minus 3. And then we need to go through and figure out what are all the different possible combinations we could get here. And I like to start just with this. Let me change colors here to make it a little more clear. If I start just with this 1 in the denominator, I'm going to take plus or minus 1 over 1, which will give me plus or minus 1, plus or minus 3 over 1, which would be plus or minus 3, plus or minus 5 over plus or minus 1, giving us plus or minus 5, plus or minus 15 over plus or minus 1, resulting in plus or minus 15. And then we're going to move on to the 3 here. So plus or minus 1 over plus or minus 3 would be plus or minus 1/3. Plus or minus 3 over plus or minus 3 we already have as 1 here. Plus or minus 5 over plus or minus 3 would give us plus or minus 5 over 3. And then last of all, plus or minus 15 over plus or minus 3 gives us plus or minus 5, which we already have. So I think we got them all right here. Okay, we don't go any further unless you're asked to, unless you really want to go to extra work. I would probably think on an exam it would be better to save time as you can for rechecking other problems or coming back to this one and making sure you got those zeros right. Okay, so find all real zeros, including multiplicities, for this polynomial function h of x equals x to the 4th plus 3x cubed minus 15x squared plus 17x minus 6. And the first thing we'd need to do here, just what we did in the last problem, is find the possible values for p over q. So if we look at the possible values for p over q, what numbers can I multiply together to give me negative 6? So 1 times negative 6, and 2 times negative 3, and you know the opposite plus or minuses of those. So we'd have plus or minus 1, 2, 3, 6. And for the q's are going to come from the coefficient on x to the 4th, which would be 1. So plus or minus 1 are our cube possible values. So if we combine all these together, we're going to end up with, hopefully you can see, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, and what we have to do to find the zeros, if we're not given a hint first, is we have to just kind of have some strategy for going through and trying zeros until we hit the right one. So let's do it. I generally start with 1. And if 1 doesn't work, I'd go on to negative 1, then 2, negative 2, 3, negative 3, 6, negative 6. In this case, let's try 1. And then we write the coefficients of our polynomial, which would be 1 times x to the 4th plus 3x cubed minus 15x squared plus 17x minus 6. If you're missing, like say we're missing x to the cubed here, I would put a 0 there just to make sure you end up with the correct answer. Okay, so we start by bringing down 1. 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. Negative 15 plus 4 is negative 11. 1 times negative 11 is negative 11. 17 minus 11 is 6. 1 times 6 is 6. We get a 0. That's what we want. That's great. So I have now factored h of x into x minus 1 times x cubed. We drop the degree 1. X cubed plus 4x squared minus 11x plus 6. Okay, but what I want to do before I go on and try another potential rational zero is to try 1 again. But now we're trying to decide if x minus 1 is a factor of x cubed plus 4x squared minus 11x plus 6, which if you look here, we already have those coefficients from our previous synthetic division. And so what I'm going to do is just try dividing x minus 1 into this polynomial by not even writing out the coefficients of the polynomial again. I'll just use what we already have. So I bring down the 1. 1 times 1 is 1. 4 plus 1 is 5. 1 times 5 is 5. Negative 11 plus 5 is negative 6. 1 times negative 6 is negative 6. And we get a 0 again. Okay, if I didn't get a 0, I'd move on to trying negative 1, but we're in luck here. So now we've actually factored h of x into x minus 1 squared times 1 times x squared plus 5x minus 6. And as soon as I hit a quadratic, I'm not going to try synthetic division anymore. I'll just go ahead and factor this using what I know about factoring quadratic functions. And so we have x minus 1 squared, and this x squared plus 5x minus 6 factors into x plus 6 times x minus 1. All right, so look, we got another factor of x minus 1. To write this h of x in totally factored form, I would probably write it as h of x equals x minus 1 cubed times x plus 6. Okay, so we have our factored version of h of x. From this, I can find the zeros and their multiplicities. So the zeros here are going to be x equals 1 with multiplicity 3, x equals negative 6 with multiplicity 1. I found that negative 6 by setting x plus 6 equal to 0 and solving for x to get x equals negative 6. So this is the answer here, and we should be good. Let's go on and look at our next problem, which is to find all complex zeros. So up to here, we've only been looking for real zeros, but we also cover complex zeros in this section. So to find the complex zeros here, this is a function that I could use synthetic division on. I could look for potential rational zeros, but it looks easy enough to factor without doing that I think I'll go ahead and just factor this, starting with factoring it into x squared minus 4 times x squared plus 4. And then I can see it's fairly easy to factor x squared minus 4 into x minus 2 times x plus 2, where we can't really factor x squared plus 4 over the real numbers. But what I'll do then to find the zeros, to find all these zeros, what we do to find zeros for a function is we set that function equal to 0. We set y equal to 0, if you think of it that way. From setting y equal to 0, or our function equal to 0, we solve each factor by setting each factor equal to 0. So we have x minus 2 equals 0, x plus 2 equals 0, x squared plus 4 equals 0. From the x minus 2 being equal to 0, I get x equals 2. From x plus 2 equals 0, I get x equals negative 2. And if x squared plus 4 equals 0, I'll subtract 4 from each side to give me x squared equals negative 4. Then x would be equal to plus or minus the square root of negative 4, which is plus or minus the square root of -1 times the square root of 4. That would be plus or minus I. Remember, I is the square root of -1. It would be plus or minus I times 2. When we have a constant, we usually write it as 2i. We would write this. We would have x equals -2i, and we would have x equals positive 2i. All right, and those are our 4 solutions. Now we want to form a polynomial with real coefficients in degree 3 that has zeros 3 and 2 minus I. Okay, so let's see what we need to do here. If I have real coefficients, I see that I have a 0 of 3 and I have a 0 of 2 minus I. In order to have real coefficients, we have to have a third 0, which would be the conjugate of 2 minus I. That would be 2 plus I. Okay, so I've got 3 zeros here. Our polynomial, I'll just call it P of x. Our polynomial P of x would be a, some constant a, times x minus 3 times, and this is how I would write this if you're solving this problem on an exam. It's a better way of getting the correct answer. If 3 is a 0, x minus 3 is a factor. If 2 minus I is a 0, x minus 2 minus I in parentheses is a factor. If 2 plus I is a 0, x minus, well, just a sec, mess that one up. If 2 plus I is a 0, then x minus 2 plus I in parentheses is a factor. And I'm just going to let a be equal to 1. It's as easy as anything, and there's no special requirements here where I have to let a be equal to something different. I write x minus 2 minus I as x minus 2 plus I. I write x minus 2 plus I is x minus 2 minus I. And I would always start by multiplying these I factors together. If we do that, we're going to have x minus 3 times, I will first of all distribute this x through. So I have x times x, x times -2, x times -I. That would give me x squared minus 2x minus ix. Okay, and then I'm going to move on to the -2. I take -2 times x, which would give me minus 2x. -2 times -2 will give me plus 4. -2 times -I will give me plus 2i. And then we'll move on to that plus I there. Let's see. So now we're at plus I. I multiply I times x, which will give me plus ix. I times -2 would give me minus 2i. I times -I would give me minus I squared. Now at this point, you should be able to cross out some stuff. Let's see what we can cross out here. We have minus ix plus ix. Those add to 0, so we'll cross out those terms. 2i minus 2i adds to 0, and now we'll see what we're left with. We have x minus 3 times x squared minus 2x minus 2x gives me minus 4x, and then plus 4. Remember, minus I squared, this is the same as minus -1. I squared is equal to -1, and so would equal positive 1. Minus I squared is equal to positive 1. We have 4 plus 1. That gives me plus 5. And now I multiply x minus 3 times x squared minus 4x plus 5, starting by multiplying through by x here. X cubed minus 4x squared plus 5x, and then multiplying through by -3 minus 3x squared plus 12x minus 15. We end up finally with P of x equals x cubed minus 7x squared plus 17x minus 15. And that sounds like what I got earlier when I worked this out. Let me double check. It is sometimes easy, depending on how things are going, to make mistakes on these. So it looks good. I think we've got one more problem, and then we'll be good. So we want to find the domain of the function f of x equals the square root of x squared minus 9. I put this in here instead of an inequality. And so you might go back and find some other inequalities in the lessons. But actually this, if we're trying to find the domain of f of x equals square root of x squared minus 9, then whatever is underneath this root has to be, underneath the square root, has to be greater than or equal to 0. So I have an inequality here that I'll need to solve in order to find the domain. To find the domain here, so when I have an inequality, I like to get 0 on the right side. We already have that here. And then I'm going to factor the polynomial inequality on the left side. And in this case, x minus 3 times x plus 3. I like to give my polynomial a name. Let's just call it f of x. Okay, so if my polynomial here is f of x, I'm going to look at each factor of f of x, set each of those factors equal to 0. And from that, I get x equals 3, and I get x equals negative 3. And then I'll solve this using a sign line, where I'm going to throw the zeros on there, the zeros of f of x, starting with negative 3, then 3. I'm going to make a note that each of these is a 0. And then I'm going to test a number in the region separated by those zeros. So to the left of x equals negative 3, I might test x equals negative 4. Between x equals negative 3 and x equals 3, I like to choose x equals 0 when possible. And then to the right of x equals 3, I can pick any number there. Oh, let's do x equals 10. Okay, just to be different. Okay, so let's start by looking at x equals negative 4. And let me change colors here. To test x equals negative 4, I'm going to come up here to my function, and I'm going to plug negative 4 in for x. So if I have negative 4 minus 3, all I'm looking for is to see that that resulting value is negative. And then if I have negative 4 plus 3, I can see that I have a negative factor there as well. So if I'm taking a negative number times a negative number, I don't care that much what the numbers are, but I can see that the result will be positive here. And that's what I'm interested in. So if I look at my test value of x equals 0, and then I plug in x equals 0 here for x, I have 0 minus 3 times 0 plus 3, or a negative number times a positive number. If I take a negative number times a positive number, that's going to give me a negative number. Okay, so all the y values between x equals negative 3 and 3, the function values will be negative. To the right of x equals 3, we're going to test x equals 10 to see what we've got going on there. So, wow, I didn't even need to change anything there, huh? I can actually just write this as 10 minus 3, 10 plus 3. 10 minus 3 is positive, 10 plus 3 is positive. So to the right of my 0, x equals 3, all my function values are going to be positive. All my y values will be positive there. So if I'm trying to find the domain of this function, what am I looking for? I'm looking for values that are greater than or equal to 0. That means positive values are greater than 0 and zeros are equal to 0. So my answer for the domain here is I'm going to include all numbers to the left of negative 3, including negative 3. So that would be negative infinity to negative 3. I want to put a square bracket there to indicate that negative 3 is included as part of the solution. Then union 3, again with a square bracket, to infinity. This would be my solution. This is the domain of this function, f of x. And with that, I believe we finished everything we need to take care of. And so have a good time studying for this exam. I hope this review helps. Send me questions if you have them. Other than that, I will hope that you do great.